Hello, welcome to Mental Reps. I'm Fish.
And I'm Ben. We said we were going to do it. We're doing it. Not week, but I almost said last week, last episode, we talked about nuclear fission and Chernobyl and all that awful stuff. Even though nuclear fission is really awesome. Yeah. Today we're talking about nuclear fusion.
We're back at it again.
We're staying on physics. We're staying on nuclear. This one is way different than they've both got nuclear in the name, and that's the only thing that's similar about them. So we're going to get right the freak into it. So we first need to really get our terms and definitions down if we're going to understand anything at all. We did this a little bit last time, but we're gonna dig into it a little bit more.
Well, because the thing about fission is that there's a lot to it. There's a lot of things that conceptually you can understand, not understand. But with fission, you can kind of just reason your way through it a little bit. Mm-hmm. I think something like this is a little more difficult. Maybe even a lot more difficult.
Yeah. You
don't need to know super intricate detail about the kind of nuclear physics side.
It's easy to paint a mental image of what's going on with fission. I think it's really easy to do that. With this, you can still do that, but you gotta have more of an understanding to be able to paint the image. Right. At least for me. So things that are going to become very relevant very quickly are what an atom is, radiation, different types of isotopes, ions, which are a specific type of charged particle, molecules, more or less, and plasma. So I did a mock-up drawing here of a periodic element of oxygen. So on the periodic table, you've got a big letter, sometimes two letters. That's your element. I wrote here oxygen. Oxygen's element letter is just O. Big O. Big ol' O. Mm. In the top left of it, it's you'll have its atomic number. That is how many protons are in the nucleus of the atom. And we'll describe what the nucleus is in a moment.
We talked about this last time. Is it protons or protons and neutrons?
The atomic number is protons. The isotope is both.
Okay, yes. That's
so
right.
There's also another number on the periodic table, sometimes above the atomic number, called the isotope. In oxygen's case, it is 16, which would just be described as oxygen 16 or O16. That is the amount of protons and neutrons in the nucleus combined. Underneath it, the name fully spelled out, which is just oxygen. And underneath that, on the very bottom left-hand side of the periodic table, is the atomic mass units. This is how much, more or less, how much this thing weighs. Its mass.
Right.
So,
well, because there's a difference between weight and mass.
There is a difference between weight and mass. Exactly. Something with the same mass can have a different weight relative to another mass. For example, 1 kilogram on Earth is not 1 kilogram on... well, it is still 1 kilogram on the moon, but it doesn't weigh as much on the moon as it does on Earth.
Well, I mean, weight is relative to gravity.
Yeah.
And mass is
mass
not
is constant.
Yeah.
Regardless of gravity. Did you know that isn't a word? Irregardless? It's just regardless.
Who said irregardless?
I just did a second ago.
Oh, okay. Is that doesn't seem like a word. It seems like regardless is the word. Is that what you're saying?
Yeah. Regardless is the word, but for some reason I do find myself saying irregardless sometimes.
Is it this is completely off subject, but it's any way, not any ways, right?
Yeah, there is no S. That one I have no problem with. I always say anyway.
Okay, that I see when I hear people say anyways, it kind of makes me cringe a little bit. And I don't.
I think about it. When people say I think about it.
Anyway, so I wanted to clarify that because I always thought it was anyway and not anyways, but so it's regardless, not irregardless.
Yeah.
Okay.
There is no such thing as irregardless.
I'm glad we nailed that one down.
I think if people combine it from irrespective, perhaps
that's just not a word I use. I don't. Irrespective.
But irrespective can also mean the same thing as regardless of. So maybe there's some sort of conflation going on there.
Yeah.
That's not something I consciously think about when I say irregardless, but that's just a guess. Anyway, atomic mass units. So the atomic mass unit of oxygen is 15.999. Now, that's odd. A lot of elements have these atomic mass units that are 2, 3, or 4 different decimal places out, rather than a full number, an integer. But the reason for that is because that is the weighted average of all the naturally occurring isotopes of the element. So a different isotope would have different amounts of neutrons in it,
Right.
which changes its mass. So the naturally occurring isotopes get a weighted average, and then that's your atomic mass unit for the element. So that's why it's not just an easy number of like 15 or 16
For the mass.
for the atomic mass unit. Yeah.
Okay. Huh.
So
That is, I did not know that. I was thinking about we talked about last time,
just throw the pen on the floor. Why don't you?
that's on the floor now. We were talking about touching on the subjects, like the isotopes of uranium and the isotopes of xenon.
Yeah.
I didn't know that. That's interesting. So I knew they had different masses. I didn't know that difference between the number and the mass. I thought the isotope just correlated to the mass only.
No.
Interesting.
No, not at all. So that's how you read a periodic table, and now let's start to actually get into what some of these things mean a little more in detail. So an atom, this is what everything is made up of. There is nothing, at least in our daily life, generally speaking, that is not mostly made of atoms. There are some exceptions, one of which I will show in a moment. But what an atom is 3 main components, 3 primary components. As we said earlier, there are protons and there are neutrons in what's called the nucleus. And this is why the nucleus is relevant to nuclear energy. It's because the energy is stirring up the nucleus, messing up with all the protons and neutrons in the nucleus. But there is a third particle around the nucleus in what's called an orbital, called an electron. It is hundreds of times less massive than a single neutron or a single proton. And that is the thing that is relevant for chemistry, for chemical reactions, are your electrons. Generally speaking, an atom has an equal amount of protons and electrons, because protons are positively charged and electrons are negatively charged. So they, just like a magnet with electromagnetism, they suck to each other. Now, you would think that, okay, then why don't the electrons just immediately fall into the protons? And that's because of the electrons aren't actually in an orbit around the nucleus. They are in a quantum superposition of all places around. This gets crazy complicated, and I'm going to be honest, I don't fully understand it. But loosely speaking, the electrons are in what's called a quantum number, which is a certain energy state, and their orbital is a cloud of probability on where the electron might be found should we measure it. But until we measure it, it is in all of those states, and it is not actually orbiting the nucleus, because then it would irradiate its energy away immediately and destroy itself, and nothing would exist. So, let's see. Of all the atoms, there are 118 known different types.
Oh.
Now, like I said earlier, what makes up the element is the amount of protons in the atom. So the reason that everything can be made up of atoms and still be different things, like metal or wood, is because of how many protons are in it. So oxygen has 8 protons. Only 94 of the 118 types of elements that we've found are naturally occurring. So there are several other types of atoms that we ourselves have created that are stable.
What might be an example of that?
I have no idea, but there's a giant periodic table that'll tell us that very thing.
There is. What was it called? Shout out?
Oh, yeah. ptable.com is an outstanding periodic table. It's got a tremendous amount of information. Of the ones that are not naturally occurring,
Full screen this.
like these are elements that we don't even have like full data on. We haven't researched them. I say we, I'm not doing anything, but people who are smart and in positions of academia. There are things that we don't know about these isotopes.
Darmstadt. The DT is getting me. Darmstadtium.
Yeah, Darmstadtium.
Darmstadt.
Something like that. But anyway, that's a extremely heavy atom because it has 110 protons in the nucleus. Super heavy atom. So, let's see. Yeah, only 94 of these suckers are naturally occurring. So if the number of protons in the nucleus change, which does happen, then the element changes. So for example, our oxygen example, if we were to pluck a proton from oxygen, it would literally just change into nitrogen. It would turn into it because it now has 7 protons in the nucleus. And if we pluck a proton from that, the nitrogen would become carbon. So this is literally the Legos of the world. We can literally just play Legos with elements in our universe, which is wild.
Well, okay. But like, can we? Is that like a thing that practically...
The laws of physics allow it, but the engineering challenges to actually treat atoms like Legos would be nothing in our children's or grandchildren's lifetime.
This might be too big of a question, or it's super simple and I'm just an idiot. But I'll ask it anyway, even though it's on a wide spectrum of possibilities. It's really in a superposition if you really think about it.
It's superimposed.
But like... the protons of the atom, right? Mm-hmm. Determine what it's going to be.
Yeah.
Why can such one being removed make something so vastly different than it would be otherwise? What is the mechanism of that?
Well, the thing is, if you remove one or add one proton, it doesn't become so vastly different. Oxygen and nitrogen aren't that different. They're both gases, right? They both have similar, liquid points, liquid temperatures. They're not that different. And same goes for something like, if we go up to a heavier element, gold has the atomic number of 79. There's 79 protons in the nucleus of gold. If we pluck one away from gold, we get platinum. It's not the same thing, but it's still a really hard, heavy-ass metal. It's not that different.
Okay.
So there aren't dramatic changes. Dramatic changes come when you start plucking 4, 5, 6 protons from the nucleus.
I guess the question then becomes, what is the proton doing?
What role is it playing?
Well,
this gets into stuff that later on we'll get into the actual contents of protons and neutrons and what they're made of. Which is, a proton is made of a up, down quarks, an up and up and a down, and a neutron is made of an up, down, and a down. And those quarks are held together by what's called gluons. And this stuff, as soon as you start digging into the atom particles, my God, the complicatedness starts skyrocketing into infinity. Yeah. So I tried to really understand the mechanisms behind how these things work, and I got a little bit of ground, but I'll talk about it a little bit later on, but it's still pretty beyond me. But basically, the proton being an up up and a down quark, the quarks are everything.
Yeah.
Given that there's 3 quarks that make up a proton, why having an up and a down quark and additionally another up and a down quark makes another element? That part is, I don't know.
But you can have protons with different quark statuses?
No, then it's not a proton anymore.
Okay, so that's where we draw the line. They have to be a certain kind of quark arrangement.
Yes.
Okay.
Because if it becomes an up, down, and a down, it becomes a neutron.
Gotcha.
And as we'll see, that is pivotal for that idea, that concept, this quark concept is pivotal for fusion.
Speaking of pivotal, I need more coffee.
So, yeah, we'll get into some quarky stuff later, but so that's the atom. That's your atom. Oh, also, atoms can be unstable if you because protons are positively charged and there's a lot of protons in the middle. You'd be like, why are they not repelling? Why are they not splashing away from each other? Well, part of it is because neutrons also add to what is called the strong nuclear force. It is what holds the nucleus together. Now, this force is profoundly powerful, profoundly strong, because if you get 2 individual protons, when you get them very close, it's what's called the Coulomb barrier. Mm-hmm. That's the barrier that is where the electromagnetic repulsion is at its strongest. 2 individual protons will repel with the force of about 50 pounds. Imagine 50 pounds of force on an individual proton. That's the size, like, now imagine 1,000 protons, or let's say, imagine 1 billion protons. Mm-hmm. Then we're starting to get to, like, maybe the tip of a ballpoint pen.
Yeah.
Okay. Now multiply that 50 pounds by that many protons. If you tried to smash a ballpoint pen together, that is an unconceivable amount of weight to try and smash them together.
Yeah.
That's how much repulsion there is from electromagnetism when you try to smash these things together. So you'd be like, well, how are they together then? And it's because of the strong nuclear force. This force is extremely powerful, extremely strong. But its distance is about a femtometer, which is about the width of the nucleus. A femtometer is, gosh, I just looked this up. I think it's a quadrillionth of a meter.
Femto,
yeah. So the strong nuclear force, profoundly strong, but it doesn't extend very far, where electromagnetism technically extends across the entire universe.
It's a thousandth of a picometer.
And a picometer is a trillionth.
Yeah.
So it would be a quadrillionth.
Yep, that's right.
Okay, so a femtometer is 1 quadrillionth of a meter. That's about the width of a nucleus. So to get these things to stay together, you have to get them over this Coulomb barrier of electromagnetism to get the strong force to start to take over. And even 2 individual protons, if they did that, the strong nuclear force isn't strong enough. That's why you need neutrons, which are neutrally charged. They have no charge. They don't repel, to add to this sort of clumping. Mm-hmm. So that's how atoms can be unstable, is a difference between the amount of protons and neutrons. Now, there can be differing amounts of neutrons compared to protons and it still be stable, but that number has to usually be a bit... the isotope has to be a higher atomic number, generally speaking. So that brings us right into radiation. So there are multiple types of what's called ionizing radiation, and we will get into what an ion is soon. But ionizing radiation can involve an alpha radiation or an alpha particle. This is when an atom is unstable, it's in a high energy state, and it wants to crap out some of its protons and neutrons. And it does just that. It emits 2 protons and 2 neutrons in its own nucleus. Now, this alpha particle doesn't have electrons associated with it, so it's not an atom. It is simply just, 2 protons and 2 neutrons would be a helium nucleus. But it's not helium because it doesn't have its electron to go with it. It's 2 electrons. So it craps out this alpha particle and just shoots it off into no man's land. There's also beta decay, or beta radiation. There's beta positive and beta negative radiation. So this is when a neutron, or a proton, but usually a neutron, decays into a proton, electron, and an antineutrino. That's called beta minus decay. So beta plus decay is the opposite. A proton decays into a neutron plus a positron, which is the positively charged antimatter of an electron, and a neutrino.
Yeah, you're gonna have to break that down a little bit if you can.
So every particle has its antiparticle. There is an antimatter for everything.
Right.
A electron being negatively charged, its antiparticle would be a positron, a positively charged electron.
That makes sense.
So if the two combined, they would annihilate and just poof into energy.
Yeah.
So that's beta radiation. Gamma radiation. This is what most people are most afraid of. So when a nucleus is in an excited, high-energy, unstable state, it will emit energy by way of a gamma photon. This usually happens alongside alpha or beta decay because of kinetic energy. So gamma radiation isn't the emission of more particles from the nucleus. It is when the nucleus is usually full of kinetic energy, which is just the energy of motion, and it's jiggling.
Yeah.
To keep itself from jiggling, it will emit energy by way of light. But the light is so high energy, it's gamma light. It's gamma rays. So the reason this happens alongside an alpha and a beta decay is when an alpha decay happens, the nucleus shoots out 2 protons and 2 electrons. Now the original nucleus of the element is in a weird orientation. So the atoms, the protons and neutrons have to rearrange in the nucleus to become in a stable state. It's like if you had a ball of let's say there was a ball of ping pong balls all clumped together, and you throw 4 ping pong balls off of it. Yeah. Now there's a chunk in that ball of ping pong balls. Because of the strong nuclear force, they're all going to rearrange to become a little bit... the total ball is going to be a little bit smaller, but that little hole that just got emitted out is going to get filled in.
Right.
That rearrangement energy causes kinetic energy because of movement.
Right.
And that kinetic energy has to get radiated out somehow by way of a gamma photon.
Okay, yeah.
So that's why a gamma photon usually comes with an alpha or a beta decay. And also, the most common form of radiation in regards to nuclear fusion and fission is just free-balling neutrons. Neutrons be flying around, hitting stuff.
And they go fast.
Yeah, and they're fast as frick. So these can just fly around all over the place because they are of neutral charge. They are not repulsed by electrons, and they are not attracted by protons or vice versa. They just fly through whatever. So when there are neutrons flying all over the place, they can smack into other nucleus, generating or converting a profound amount of kinetic energy to that nucleus, which we now know when a nucleus has a bunch of kinetic energy in it, it wants to get rid of that. So it's going to emit gamma rays or just decay into something lighter and emit all sorts of radiation.
Yeah.
So that's why free-flying neutrons are very bad. Very bad. All right. So that's radiation. So let's get into what exactly the isotope of something is. We already discussed this a little bit, so we don't need to linger on this too long. But an isotope is a version of an element, the same element with the same number of protons, but a different number of neutrons. So the number used to express a specific isotope is the amount of nucleons, which is just nucleus particles. Nucleons is a category, not its own particle.
Oh, okay. I was going to say, I'd never heard of that, but that makes sense.
Yeah, nucleons are just a category of nucleus particles. So when we talk about last episode, we said xenon 135 a lot. That got thrown all over the place. So xenon 135 is equal to 135 nucleons, which is just particles in the nucleus, which is the same as 54 protons plus 81 neutrons. So, but we know that xenon 135 is radioactive. It's not stable. It will decay in about 9.2 hours.
Right.
So 54 protons plus 81 neutrons is not a stable combination of protons and neutrons. All right. So now these radioactive decays can get crazy. So as we just said, xenon 135 will decay into cesium 135. It undergoes beta decay. So beta decay was this would be beta minus decay. A proton turns into a neutron and emits an electron and an antineutrino. So because a proton goes away, the element changes.
Right.
And a neutron gets added to the nucleus. So xenon 135 can go into cesium 135. The number would stay the same, but
because it's the same amount of
nucleons.
Nucleons. That's the
exactly.
word. Yeah.
But there's one less proton, so it turns into cesium. So when the xenon 135 beta decays, it changes its element. Now, like I said, these radioactive decays can get crazy when something of a lot of nucleons decays into something that is still unstable, that decays into something that is still unstable, and so on. So uranium-238 is one of these very isotopes. Uranium-238 can undergo 14 decays before it turns into lead-206. And it takes a while. So uranium-238 is technically radioactive. So it's not safe technically, but its half-life is 4.5 billion years.
Jeez.
So uranium-238 takes a while. And when it decays into thorium-234 because it undergoes an alpha decay. It emits 2 protons and 2 neutrons. So U-238 goes into thorium-234. Thorium-234 is still radioactive. It undergoes a beta decay into protactinium. God, that was a tough one. Protactinium-234. That decays in about 6.7 hours. Protactinium-234 decays into back to uranium.
Oh.
It turns back into uranium-234.
Oh, okay.
So uranium kills itself, turns into something else, which kills itself, and then it turns back into uranium. Given enough time, uranium will change and then go back to uranium. That's freaking crazy, first of all.
Yeah.
That an element can just turn into something else and then it just turns back into its thing again. That's wild. So, but it's still radioactive. So that uranium-234 decays into thorium-230 after about 250,000 years.
Okay, yeah.
That decays into radium-226 after about 76,000 years. That decays into radon-222, which decays into polonium-218, which decays into lead-214. We're at lead, but we're going away from lead because that's a radioactive isotope of lead. Very radioactive, mind you, because that decays in about 3 minutes. So that decays into bismuth-214. Bismuth sounds right. Bismuth-214. That decays in about 20 minutes to polonium-214, which decays in about 20 minutes to lead-210. We're back at lead again.
Not very long.
Not for very long. After about 164 microseconds, that decays back into bismuth. We're back to bismuth, baby. And it stays that for about 20 years.
Yeah.
Nice and long. Stays bismuth for about 22 years. But that decays into polonium. We're back to polonium-210. That decays in about 5 days. And then we're back to lead-206, which is stable. That's insane.
Wow. And it's funny how different these time frames are, because like you'll get thousands and thousands and thousands of years, and then it's like 20 minutes.
Exactly. Yeah. The uranium-238 stays 238 for 4.5 billion years, and then the freaking, what was it? Yeah. Bismuth-214, or excuse me, polonium-214 decays into lead-210 in 164 microseconds.
Yeah.
Like, and we get we get uranium turning out of uranium back into uranium. We get polonium going away from polonium, turning back into polonium, and then going away from polonium and turning back into polonium again. Lead, polonium turns into lead, which goes away, but it comes back for 164 for 22 years, and then it goes away again, and then comes back as stable.
Yeah.
Like, this is insane. This is literally like Legos jumping off of each other and collecting. Like, this is nuts. This is nuts that our world can do this, where things can just turn into other things and then back to the same thing with a different amount of neutrons and protons. Not protons, different amount of neutrons. Crazy. So radioactivity is insane. And it's dangerous. Sometimes. Not always. It depends on which one we're talking about. All right. Let's talk about ions. We talked about these earlier. All the radiation that is ionizing. That's the dangerous radiation. Mm-hmm. What does that actually mean? So an ion is an atom with a positive or negative charge. So, as I said earlier, the amount of protons is usually matched by the same amount of electrons to match the charge. If you have 10 positive protons, generally speaking, you're going to have 10 negative electrons, making the atom as a whole neutral charge. Mm-hmm. An ion is when an electron gets stripped off or added to the atom. So if an electron gets pulled away, the atom is now positively charged because there is more protons than electrons.
Sure. And
the opposite is true. So this is what causes adverse health effects in you. If atoms inside you are ionized, that is what causes big problems. It can destroy cell structures. If one of your DNA molecules gets ionized, you're fricked. That thing's going to mutate, usually, eventually, into cancer. That's how radiation causes cancer. So ionizing radiation is the big thing with us. If our atoms get ionized, if there's not very many of them, our bodies will just fix it. But if there's too many for our bodies to repair, that's when problems start happening. So what is a molecule? A molecule is two or more atoms where the electrons, the outer specifically energy state of electrons interact. Those are called valence electrons, forming chemical bonds, resulting in a more stable, lower energy configuration than the atoms individually.
I haven't heard that term in so long. Valence electrons. I just had a flashback to like high school physics. And I remember hearing that term, and then I was like, I'll never freaking hear that term again. And I just did. And I was like, I remember that.
A valence electron is the outermost energy state electrons. And those are the ones that are relevant for chemistry. And chemistry, a chemical bond is what we call a molecule. So a molecule is more than one atom, because an individual atom is just an element. But if you get two or more atoms bound together chemically by these valence electrons, you can get something like water. So a molecule is a single molecule is the smallest amount of atoms, or not atoms, the smallest amount of a thing and still be that thing. So water does not start being water until you get, well, everyone knows the molecular structure of water. H2O, hydrogen atoms, 2, and an oxygen atom.
Yeah.
So until you get 2 hydrogen atoms and an oxygen atom combined, now that's water. But as soon as you pull one of those off, it's not water anymore. But that's the smallest amount of water you can possibly have, is 3 atoms. And once you start adding more of those chemical bonds, you get flowy wetness. So that's what a molecule is. So that's why there are more things, as it would seem, than there are just elements in the periodic table, is because these elements can combine to form chemical bonds, which create other things.
Yeah, water is not on the periodic table.
Water is not an element. It is a molecule. It is a combination of elements. All right. Now we got plasma. This is the one real relevant to fusion. Plasma. So this one's crazy. There are 4 states. There is solid, there is liquid, there is gas, and these are all temperature related. There is solid when it's coldest. Different elements have different temperatures for this requirement, for this measurement, but when it's coldest, it's solid. When you raise the temperature, it becomes a liquid. Mm-hmm. Even if it's concrete, it's going to become a liquid with a high enough temperature. Anything will.
Yeah.
When you raise the temperature, you get gas. That liquid starts poofing away. When you raise the temperature past gas, that's when we get plasma, baby.
Okay. All right.
That is the 4th state. And plasma is over 99% of the universe.
That's hot.
That's hot. That's Most of our universe is in a plasma state. Most of our lives, in fact, a minute fraction of our lives is not a plasma state.
Right.
We don't deal with plasma usually. We don't see that stuff usually because you have to get to thousands of degrees for plasma to.
So, what exactly is plasma?
So, when you keep raising the temperature, what happens is the electrons on the outside of the atom start getting thrown off. And the reason that
they don't like that. They don't like that.
They don't like that. They don't like heat. And the reason why is heat is a measurement of the average kinetic energy in a given system. Mm-hmm. So when you have something that is butt loaded with kinetic energy, the movement energy, the jiggling, that is what creates heat. And when there's so much kinetic energy, what's going to happen is those electrons are going to get bumped off.
Yeah.
Because there's so much freaking movement.
They just can't
stay
They
on.
couldn't hang with it.
They couldn't hang with it. So that's why high temperature can knock off these electrons. And what plasma is a free-flowing soup of ions. Because the electrons fly off, all of these things are positively or negatively charged. You get a bunch of nucleus that don't have electrons, so they're positively charged, and you get a bunch of electrons flying around that don't have a nucleus to attach to, that are negatively charged. So you get this soup of charged particles, electromagnetically charged particles, and that's going to be relevant in a moment here. But that only happens if you have a profound amount of kinetic energy, which is just temperature. Now, I have plasma here with me.
Oh, okay.
You want to guess what this is? How it's possible that I can just have plasma here with me?
Freaking.
Here's a hint. Lightning is plasma.
I don't even know where to start with a guess on this. What?
You'll know exactly what it is and how I'm talking about it as soon as you see it.
I couldn't fucking.
Okay. All right. We've got plasma here.
Oh, it's one of them things.
Yeah.
It's one of them.
This is plasma.
I want to touch it. Them things are cool.
Yeah. Everybody knows what these are. These are sick. These are freaking sick.
Well, for the audio listeners, why don't you explain what you're holding?
Yeah. I'm just guess. Yeah. So
all you need to know is these things are freaking cool.
Yeah, don't you know what I'm talking about? Yeah. So what I'm holding here is a glass ball that has a coil in the middle of it that is causing a reaction, creating plasma. And it's like a lightning ball. It's like a ball of lightning. If I touch my finger to the outside of the glass, all the lightning gets sucked to my finger, right?
Yeah.
That's because there's a lot of negatively charged electrons on the outside of my finger here that this is getting attracted to because electrons are protons are positively charged. They're going to get sucked to electrons. This is plasma. Now,
what exactly is plasma in there? What are you talking about when you say that?
This is just positively or negatively charged particles. This is not atoms. It's like lightning.
You're talking about the thing that you're seeing, the phenomenon you're seeing inside.
Yeah.
Okay, yeah.
Yeah, these are not atoms in here.
Gotcha.
So, and the reason this happens is because of electromagnetism.
Mm-hmm. Yeah.
It's like magnets. So, we can see that if we have something, if we have something that's charged, like the ends of our fingers with negatively charged electrons, we can control this plasma. Sort of.
Yeah, it's still
pretty wacky.
It's still kind of freaking out.
Yeah, but we can make it a little bit more stable than it would be on its own. So that's fuck. I just smacked the microphone stand. That's analogous to what we're going to talk about in fusion power plants. Now, I will say, plasma has been generated before humans ever came to the scene on Earth, obviously in stars, but on Earth, there's an animal that generates plasma. And because you've read the note, you know the answer to this. But guess what that animal that generates plasma is?
It's got to be dogs.
Exactly. No. There is an animal called a pistol shrimp. A pistol shrimp. Its claw clamps so fast and with so much force that for a moment it creates plasma in its frickin' claw.
Yeah.
And it creates a extremely loud noise like a pistol. That's why they called it that. And it uses this claw to stun its prey and eat it.
It's just a little guy.
It's tiny. It's tiny. But this thing creates plasma. That's crazy. It's a shrimp. We have been outdone by a shrimp.
Is it edible? Can I eat it?
Can we eat pistol shrimp? I don't know.
I don't know.
Is it going to plasma your insides?
Can you eat pistol?
Can you eat pistol? Can you eat pistol? Can you eat pistol shrimp?
How to feed pistol shrimp? That's not what I want to know. Google AI says yes, you can eat pistol shrimp.
Nice.
But it's not common and comes with important caveats. Oh.
Is it going to let off a round when it's inside you?
They're not commercially available. Well, that doesn't matter. I'll go find them.
If they don't stun you with their plasma weapon.
I don't care about caveats, and I'm going to say publicly that you can eat these.
All right. I'm not as part of this. So let's get into the physics. Let's get into the physics of fusion. Mm-hmm. We understand the molecular structure. We understand of an atom. We understand subatomic particles somewhat. We understand chemistry. So let's talk about how this can be used to generate energy. All right. Fusion is when two nuclei fuse together to become one. Mm-hmm. And we know how this can happen. We already discussed how one element can turn into another element and back and forth and up, down, left, right, mid, center, top, down.
Yep.
So this seems intuitively possible. But the problem is, what I mentioned earlier is getting over this column barrier. This immense amount of repulsion from the positively charged protons that don't want to stick together. Excuse me. All right, but if we can get atoms to fuse, it releases a nutty amount of energy, insane amounts of energy. Mm-hmm. So, but only if the resulting nucleus is more stable than the previous two nuclei on their own. If the resulting nucleus is not more stable, then it actually absorbs energy and doesn't release energy. And the reason that is, don't ask.
Oh, okay.
So
I didn't even wonder. So
Well, this is where the really tough stuff starts getting into it. So, the reason why is it results in what's called a mass defect. Okay, where the fused together nucleus has less mass than the nucleons individually. Mm-hmm. Where did that mass go? Okay, that's that mass gets turned into energy. This is what I was talking about last episode. E equals mc squared. Energy is equal to mass times the speed of light squared. But the mass... okay, this is where it gets crazy. This is insane. So I don't understand this fully, so I'm going to caveat this. Most of my research time for this episode went into this part alone, and I still barely understand it. So... the mass isn't just, it's not just some magical stuff, okay? The mass defect, the energy is coming from the nuclear binding energy. So, as I said earlier, there's a strong nuclear force that is extremely strong, but extremely short range. There is less nuclear strong force needed to hold together a more stable nucleus than a less stable one.
Okay.
So, because there is less nuclear binding force or energy needed to hold together this more stable nucleus, the excess that was needed to hold together the individual nucleons on their own gets released as energy. So what is the strong nuclear force made of? I asked myself this question. Don't ask me. But well, if you do ask me, if you haven't asked me, don't, but go ask someone smarter. But if you do ask me, my very loose understanding of it is the reason an individual proton would even have any nuclear binding energy at all is if it's made of something else. Which it is. Quarks. Mm. The quarks are held together by gluons. Gluons are the strong nuclear force, I think. So there are less gluons needed to hold together multiple stable nucleons than there is nucleons individually. And these gluons are what cause this mass or energy defect when a more stable nucleus is the end point. And the gluons being released as the strong nuclear force is what we call nuclear energy. It's all in the gluons, basically, that hold together the quarks that make up the protons and the neutrons.
Okay. That kind of makes sense. It's kind of a zooming in kind of a thing. Like it's profoundly more complicated than that.
Yeah. Like I said, I barely understand it. But as far as I know, that's the rough and tough of it. But basically, when two nucleons come together to fuse one, energy gets released. Mm-hmm. That's the important part, and a lot of it. So how does this happen in stars? Before we understand how it happens on Earth, we have to know how nature's doing it on its own so easily.
Yeah.
And I'll tell you, it's not at all how we're going to do it on Earth. But the sun's core, the core of the sun, has about 150,000 kilograms per meter cubed of pressure. That's about 150 kilograms per decimeter cubed. A decimeter is a 100th of a meter. Just imagine that.
That's difficult to imagine.
Can you every 100th of a meter? Imagine on your if you and I were in the center of the sun.
Oh,
yeah, we would have every decimeter, every 100th of a meter, 150 kilograms of pressure on us. Every decimeter of our body.
Yeah.
Or if you want to say every meter, a meter is about 3-ish feet. So you and I are, roughly speaking, 2 meters tall. You and I would have 300,000 kilograms pressing against us on all sides. 300,000 kilos.
Jeez, that's a lot.
So if you and I were in the center of the sun, we would immediately get crumpled up into a tiny, tiny, tiny little ball.
Yeah.
Because if you try to imagine bench pressing, even something like 100 kilos, which is heavy as frick for me. What is that, like a couple hundred pounds?
Yeah.
100 kilos is not even the weight that would be on 1/100th of a meter on your body. So it's just like the center of the sun smashes things together so profoundly, it's insane. That is something that we can't do here on Earth. We don't have that kind of pressure. Because of all that pressure, it's about 15 million degrees Celsius in the center of the sun. 15 million degrees Celsius. That is more than hot enough to strip away any electrons from the nucleus. So the sun is all ions, which means it is all plasma. The sun is just a bunch of plasma. So the sun first undergoes a proton plus a proton fusion. Now this doesn't make sense because that's a profoundly unstable nucleus. They would immediately repel. So proton-proton fusion can't. So even under that much pressure, remember how much I said that this column barrier, even on one individual proton, it would be 50 pounds of repulsion?
Yeah.
So that, even in the sun can't even beat that. The sun can't beat the column barrier of pressure. Because even 150 kilos per decimeter cubed, a decimeter is still thousands of times bigger than an individual proton. So the sun doesn't have even 50 pounds of pressure per one individual proton size. So it can't overcome this column barrier to fuse them. So how does it do it? Well, this is another thing. Don't ask me, but if ask someone smarter. But if you did ask me, it's because of quantum tunneling. So, because of quantum mechanics, we know that individual. Stupid ass garage door. Because of.
Just give it a second.
Because of quantum mechanics. Let me just tell what happened. Our garage door is possessed. It opens and closes on its own, and it just opened. So, because of quantum mechanics, things are not... particles are in a constant state of all states at once. It doesn't make any sense, but it's just how the world works. And that also means that all the protons within the sun have a non-zero chance of being even in this room right now. Okay? Non-zero. Now, it's called a probability amplitude because it's a wave, and a wave carries energy or an amplitude, and this wave has a probability of being throughout anywhere in the entire universe. But as it gets further away from its highest energy spot, which is what we would call the proton, as it gets further away from that, it has a lesser and lesser and lesser likelihood of being over there. So there is a possibility of two protons quantum tunneling or having a probability amplitude that is close enough for the strong nuclear force to take over, to just straight up sidestep the column barrier. Now, this probability amplitude has to get this positional probability amplitude has to get stacked on top of the fact that these are both protons, and that ain't going to work. One of them has to be a neutron. So the proton has to undergo a beta plus decay.
Right.
Where the up, down quark, one of the up quarks spontaneously, because of the weak nuclear force, I don't understand it, don't ask, because of the weak nuclear force, turning one of these up quarks into a down quark, turning it into a neutron, which emits a positron and a neutrino. Mm-hmm. This we know happens because every square centimeter, all around us right now, every square centimeter, there's about 10 billion neutrinos flying through us. And those bad boys are coming from the sun because of this beta plus decay from a proton turning into a neutron, emitting one of these neutrinos. And all those suckers are coming down through us. So, those two things have to happen simultaneously. The proton has to quantum tunnel into the strong nuclear force distance of another proton, as well as this up quark has to spontaneously, because of the weak nuclear force, turn into a down quark, turning this proton into a neutron. Then you got a proton-neutron nucleus. They have fused, which will release a profound amount of nuclear energy because of the binding energy. It's less in its final state than it was individually, which creates a nuclear reaction, which powers our sun. That's only step one. That's step one. You are confused.
Well, so the things have to take place. What am I getting at here? How do you control for this happening if things have to happen in a certain sequence? You see what I'm getting at here? So with the quantum tunneling and the flipping of the quark, right? Mm-hmm. If this is the mechanism we use for nuclear fusion, how do we control this in an environment?
Well, this is the mechanism the sun uses, and we can't do this.
Okay, we're still on the sun.
This is still just the sun.
Okay, so this is not practical yet.
Yeah, this is not practical yet. Like I said, the sun's fusion is profoundly different from our fusion.
Okay, what I was confused was like, okay, this is all just probability stuff that's out of our control.
This is probability. Okay. And speaking of that probability, at 15 million degrees, at 150,000 kilograms per meter squared of pressure, the chances, so that's a lot of protons just flying all over the damn place.
Yeah.
That's a lot of them. The chances of two of these neutrons smashing into each other and the probability amplitudes lining up so that they quantum tunnel while a beta decay happens is about 10 to the negative 28 per proton collision. 10 to the negative 28 probability of that happening. That is about 0.00023 more zeros 1% chance happening.
Yeah.
That is, if there were just two protons smashing together, that would not happen for billions of years. That would not happen pretty much at all. We would never see that happen in anyone's lifetime or a billion people's lifetimes. The chances of that happening are so low. But because the sun has so many protons in its core, this happens quintillions amounts of times every second.
Yeah.
Because there's just that many protons in the sun's core. So this infinitesimally small probability chance thing happens so much, just an incomprehensible amount to create an entire sun.
Yeah.
We don't have control over that probability on Earth. So, but the sun's not done. The sun's not done. So that's just how you get a proton-neutron combination.
Right.
Okay. That proton-neutron combination is just hydrogen 2. Hydrogen 2. Mm-hmm. So once you have this proton-neutron combination, this hydrogen 2 now easily can just grab another proton. Says there's so many protons flying in that sucker, that will happen in minutes or less. So that makes it helium 3. It's helium now. 2 protons and a neutron. So we just got hydrogen fused into helium. But it's still not done. The helium-3 fuses with another helium-3. So two proton-proton neutron pairs fuse. Now you have 4 protons and 2 neutrons, which is extremely unstable, which decays in the proton neutron nucleus is beryllium-6. It becomes beryllium-6 that the helium does. That's extremely unstable. It decays in a matter of picoseconds, less than 1 picosecond, in fact, just an incomprehensible on human scales amount of time, which becomes lithium-5. It shoots out a proton, becomes lithium-5, which is still unstable, shoots out another proton, which becomes helium-4, which is stable. That is how our sun fuses hydrogen into helium, with only protons. We can't do that. Specifically, the proton-proton fuse, we can't do that. Not even close. Not only do we not have enough pressure to get these things to quantum tunnel, and even with the sun's pressure, the chance of it quantum tunneling is still profoundly low. And we have no control over when a beta plus decay would happen. Just it's all probability in the sun. Yeah. It's all probability. It's all quantum mechanics in the sun. We can't rely on probability for power generation. So let's talk about how we fuse these suckers on Earth. So generally the isotopes used to fuse on Earth are hydrogen-2 and hydrogen-3, otherwise known as deuterium and tritium. There are 2 hydrogen isotopes. And the reason we use those is because we talked about this a couple last episode, is because of the cross sections.
Yeah.
So as we know, fusion or fission is a probability, and we can increase this probability the best we can by way of a cross section. How fast these things are moving when they hit to maximize the probability that they fuse, or in the case of fission, fizzle out. And helium-2 and helium-3, or deuterium and tritium, are the isotopes that we have found that have the highest and easiest to achieve cross-section. However, we don't have the insane gravity that the sun has to get these things close enough to quantum tunnel. And even if we did, quantum tunneling is just unbelievably unlikely. So we have to basically just raise the temperature. We have to raise the temperature. We have to go up and up and up and up and up to get even more kinetic energy into these things, so that they smash together with even more force to try and overpower this column barrier. And that temperature is in excess of 100 million degrees on Earth. Now you might be asking yourself, how the frick is that possible on Earth? Where can there be 100 million degrees without everything around it just instantly vaporizing?
Yeah. What is your containment vessel looking like?
Exactly. And we'll get into that. But so 1 deuterium and 1 tritium nucleus fusion releases about 17.6 million electron volts. That's not very much. That's about the kinetic energy of a grain of sand if you threw it. That's from one reaction. That doesn't sound like very much at all. However, 1 kilo of fuel of deuterium-tritium mix, 1 kilogram of fuel is about 10 to the 26 fusion reactions from 1 kilogram of fuel. So if you multiply this 17 million electron volts by 10 to the power of 26, you get a profound amount of energy. That becomes more grains of sand than there are on Earth to throw.
Yeah.
So just from 1 kilogram of this fuel, you get an insane amount of energy. 1 kilogram of deuterium-tritium fuel would produce about 94 million kilowatt hours of energy, which could power roughly about a 100,000 population city for 2 weeks or so. A big city for 2 weeks from 1 kilogram of fuel.
Jeez.
That's nuts. That is nuts how much energy fusion creates. We would not have to worry about fuel for a very long time. Now, deuterium, hydrogen-2, is everywhere. That's scoop up a water and you got deuterium isotope. You got hydrogen-2. Tritium is harder to find. Deuterium-3, it's because it's radioactive. Its half-life is about 12 years. So most of this stuff is radiated away. We don't have a lot of tritium. We have ways of creating it, but it's much harder to find. It's a very minute fraction of the amount of hydrogen in our world. But even then, it's not really a problem because of how little we need to generate an insane amount of energy.
Right.
All right, so how the frick do we contain 100 million degrees? Like, what do we do here? So, you'll remember that plasma, anything at 100 million degrees is going to become plasma, no matter the element, literally anything. But plasma is a soup of positively and negatively charged particles. It is a soup of charged particles. Now, as we just saw with my finger touching the lightning,
Yeah.
we can sort of control where this stuff goes.
Yeah.
And if we build a circular donut-shaped device with plasma inside, if the circle is made of magnets, we can create a magnetic field inside this donut.
Mm-hmm.
And because of the plasma being charged, we can control, the plasma can be suspended in midair by way of insanely powerful magnets.
Sure. Yeah.
So it doesn't touch literally anything, because 100 million degree plasma, if it even grazes anything on Earth, it's going to get immediately vaporized. Whatever it touches is immediate vaporization.
Yeah.
So you have to keep this stuff confined in, well, it's not even mid-air, because air is a pretty bad contaminant. It has to be a vacuum.
Yeah.
You have
Suspended in a vacuum.
Suspended by magnetic fields in a vacuum. Now, it's a mixture of deuterium and tritium that's used as the fuel, and it's heated to a plasma, which is actually pretty easy, because plasma with deuterium, tritium can get heated to a plasma in only a few thousand degrees only. But to get this into the hundreds of millions of degrees, there is a beam, a particle beam shot into the donut of more fuel at very high, extremely high energies. And because we're shooting particles into an already hot soup of particles, the particles are smashing up against the particles that are already in there, creating even more kinetic energy.
Yeah.
And since we know kinetic energy equals heat, that's what heats it up even further, is insanely high energy beams of particles. That there's another way where we can shoot electromagnetic waves that are of the same wavelength of the charged particles inside there. And when that happens, the charged particles absorb the wave as more kinetic energy. So usually those things happen in conjunction. And that's how we heat these things to mind-blowing, hottest temperatures in the whole universe levels of temperature. And when temperatures are this high, you just have to keep this sucker sustained. And hopefully, the goal of doing this is what's called ignition. When there is enough fusion reactions that are releasing enough energy that the heat becomes self-sustaining. The fusion reactions are causing enough heat so that we don't have to keep pumping insane amounts of energy as a particle beam into this thing. Now, that's extremely difficult, because as we also just saw, when we touch our finger to that plasma, the plasma still kind of fricks around.
Yeah.
It's really hard to keep plasma the way you want it. It's extremely tough to be stable, because even on the edge of the sun, solar flares, those things that poof out, that's just plasma being plasma. That's plasma being weird.
Yeah.
It's super hard to control. It looks like a liquid, but it's not a liquid. It does not react like a liquid, and it does not have the same physics as a liquid. So that's basically it. There's other types of fusion generators, but the most common ones are this donut one that I referred to, called a tokamak, is what that's called.
Well, and then how do we get this fusion generator that you just described into power? What's that mechanism?
Well, the same way fission.
Well, obviously we don't do that on on any commercial scale currently.
Yeah, you're right. Right now, we don't do that.
So this is still a...
Fusion has not been... Fusion has occurred. We have created fusion, successful tokamaks. What we have not done is been able to sustain it for any decent amount of time. I think the world record right now is 22 minutes.
Well,
and even in... That, which is pretty freaking good.
Yeah.
Which is pretty freaking good. That's a long time to sustain 100 million degree plasma. But what we need is it to put out, to generate a vastly significant amount of more energy than we are pumping into it by way of heating it up. And that's the difficult thing, is getting net energy, enough net energy for it to matter, and also sustaining it for longer than 20 minutes.
Right. But if this was viable, it would still be to heat water to create steam.
Heat water, create steam, turn turbines. It's all the same stuff. Yeah.
Gotcha.
Yep. It's the same mechanism to generate electricity. There are other fusion generators that are doing it differently. One of them, basically, there's another one that's, I don't know much about this, but it's basically a particle accelerator where it smashes particles together.
Yeah.
Except it's just smashing these isotopes together. And it just does it millions of times per second, over and over and over and over and over again, and hoping fusion occurs. That one I don't know much about, but it's just another engineering, marvel. And so deuterium tritium? Deuterium is... So there's enough neutrons in here that when these things fuse, a neutron still goes out. Mm-hmm. There's still a lot of neutrons flying around here. And if you remember from earlier, flopping around free neutrons are a pretty awful form of radiation.
Yeah, we don't like that.
So this still creates radioactive material, but it's only the material walls inside the donut. That's literally it. And it doesn't generate even a fraction of as many neutrons as fission creates, which literally relies on more neutron creation. As far as I'm aware, anyway. So the amount of radioactive material this would produce compared to fission, which already isn't very much, is even way lower. As well, fission, when you turn it on, it is itself self-sustaining.
Yeah.
And if you don't, take precautions, it will, run away.
Right.
This is not that. This is... This can't... With fusion, it's impossible to make this thing cause serious damage because it's so freaking hard to get it to do what we're trying to get it to do.
Right.
It's so freaking hard to get this thing just to stay going. So it literally can't have a runaway or a meltdown or an explode. That just literally cannot happen. So it's way safer as far as like catastrophic problems are concerned.
Yeah, no, that sounds like if we can figure out how to do this sustainably, I mean, this could be a big thing for the future of energy.
Definitely. With how little fuel it takes, with how abundant the fuel is, and with how much vastly more energy it generates compared to fission, and with how much safer it is, and with how much less radioactive material it produces. This is almost like endgame energy creation. Like millions of years into the future, we'd be set if we could commercialize fusion. But my God, it is like these are temperatures and conditions that don't exist literally anywhere in the universe. This is like one of the greatest feats of engineering literally ever. Mm-hmm. If we can achieve this.
And clearly it can be done.
It can be done. We can do it. There's a facility called ITER, which is an enormous billions and billions and billions of dollars have been pumped into this. And this facility is not even trying to put energy on the grid. It's trying to just get the physics and get the engineering down.
Yeah.
And once it does, then we can start mass building these things. But here's the problem. These have the same problem with startup as fission does. It is billions of dollars to build a plant and decades of planning and preparation and construction to get these things up and running.
Yeah.
So one thing that these could be is our end game of energy creation. But what they're not going to be is helpful for something like climate change.
Yeah.
Because it's just too even if we figured out the physics now and the engineering problems now, it is decades away still.
Right.
So fission is still more practical right now because it's already class leading in terms of safety. Mm-hmm. Right? It already doesn't generate much radioactive material. It already does generate millions of times more energy than any chemical reaction and doesn't pollute our atmosphere. Fission is still absolutely the most relevant thing right now, I think. Fusion, there are billions and billions and billions of dollars that have been invested into fusion because people think it's close. It's really close. Like literally I think it was last year is when that 22-minute world record of sustained plasma was done. And I believe it had a net energy gain with it.
Yeah.
It's just, we got to keep that up for days, weeks, and months.
Yeah.
So that's fusion. Like I said, a lot of that to understand it and how it worked was physics. But I hope you got that all.
That was a lot.
It was a lot. Yeah.
I feel like I understood a good bit of that. Well, you ready to play a game?
We got a game.
We got a game here. We're going to find out today if you are smarter. You see where I'm going with this.
Dude.
If you are smarter than not a fifth grader.
Oh.
Because
please say a first grader or something.
Because I don't know if you knew this, but they're not teaching first graders a lot of physics. So
I bet they aren't.
Here's what we're going to do. I've got, just like we did when we did that full episode of this, I have 11 questions. Instead of grades 1 through 5 and then a sixth grade, you've got grades 8 through 12 and then a college level question is what you've got.
Okay.
That makes sense? So 2 questions per grade. As far as cheats go, you're just going to get, so there are 4, it's multiple choice every time. You have 3 uses of an elimination. So you've got, there's 4 options. I'm going to eliminate one of the options.
Okay. 3 uses of it?
You get 3 uses of that. The energy of matter in motion is A, electromagnetic.
Kinetic energy.
Yeah, that's right. I told you.
Let's go.
All right, 8th grade, level 2. The rate at which velocity changes over time is known as A, speed, B, acceleration, C, Newton.
B.
That's right.
Acceleration.
I told you. They're not that
okay, I'm getting
We're getting 9th grade.
Oh my God. We are flying, dude. I'm old.
The constant force of attraction between all objects with mass is called A, inertia. Gravity's right.
That should have been the freaking 8th grade one. What the hell?
Some of the, yeah, look at that. Which of the following is not an example of a force? A, tension, B, weight, C, friction, D, mass.
Not an example of a force.
Which of the following is not an example of a force?
Okay, here's the problem. Mass, some people call gravity a force, but it's not, because in Newtonian physics, it is a force. In relativity, it is the bending of space-time. Mm-hmm. Bent space-time is not a force. But that's not the colloquium. That's not high school level. So, at that point, gravity probably still is a force. Tension?
Tension, weight, friction, mass.
Friction is...
This seems obvious to me.
Not a force? I'm thinking tension.
Is that your final answer?
Well, no.
Why would it be?
Weight is just another way of saying gravity, which gravitational force, that's still a force.
Maybe another way of saying this is, and again, I lifted these from actual like test questions. So like I didn't make these up or anything.
Okay.
Another way of saying this might be
friction or tension.
Another way of saying this is which is an example that doesn't have to involve force. Tension, weight, friction, and mass.
Mass.
Correct. Yeah, because why?
Yeah.
Because weight is gravity. Friction is the repulsion, right?
Yeah.
Or not, I guess you could say that. And then tension, of course, is just tension. We all know what tension is. But yeah, no, it's mass. You're correct. You don't need to focus on what the force acting on it is to understand what the mass of an object is.
Yeah. Okay.
Okay, 10th grade.
Okay.
As the temperature of an object rises, so does the A, mass of the object, B, thermal energy of the object, C, potential energy of the object, or D, specific heat of the object.
Thermal energy.
Correct. That one wasn't that bad. If you know anything about terms, you'll get that one.
Yeah.
An example. This one's interesting. An example of potential energy is A, a basketball sitting on a rack, B, a bird flying, C, grandma rocking in her chair, and D, none of the above.
An example of potential energy.
Uh-huh.
A basketball sitting on a rack.
That's correct. Why?
Because it's being held up. It could have kinetic energy that's otherwise being stopped by the rack.
Correct. Yeah. And a bird is flying, so that's kinetic.
Yeah.
Grandma rocking is rocking, kinetic.
Yeah.
And then it's not none because it's A. Right. Perfect.
Yeah.
That is 10th grade. So 11th grade. You're doing great.
Oh, God. We're flying.
I told you, none of these are that difficult. All right. Well, we're getting there. And I intentionally chose these. A lot of these had like a shit ton of math in them. Like I didn't choose any of those because we'd be sitting here doing math for a while.
We don't need to do
And I don't know how to do any of that math. So,
We only just learned long division the other night.
Yeah. I mean, you learned. I knew it kind of.
Yeah, I learned it for the first time.
Which of the following is not true of gases as compared to liquids or solids? A, gas molecules are in constant rapid motion. B, molecules in a gas are tightly bound to each other by strong attractive forces. C, the kinetic energy of a gas is directly proportional to its temperature. Or D, the volume of a gas molecule itself is very small compared to the space the gas occupies.
Which one of them is not true?
Which one of them is not true of gases compared to liquids or solids?
Not true of gases compared to liquids or solids. What was C?
C was the kinetic energy of a gas is directly proportional to its temperature.
And what was B? I'm looking for what's not true of a gas.
B is molecules in a gas are tightly bound to each other by strong attractive forces.
Read A and D again.
A is gas molecules are in constant rapid motion. And D is the volume of a gas molecule itself is very small compared to the space the gas occupies.
D.
Is that your final answer?
Yeah.
That is incorrect.
Frick.
So the correct answer was B. Molecules in a gas are tightly bound to each other by strong attractive forces. As compared to liquids or solids.
Oh, dude, I answered yeah, okay. I answered what is true of a gas.
All right. Well, you're stupid. You want to go ahead and finish this out?
Yeah.
All right. So
Shoot, man. I didn't even freaking consider the question.
Yeah, dummy. So you're not smarter than anybody, really. So
because when you said the answer, I'm like, well, that's not true of a gas. And I'm like, yeah, idiot.
That's one of them trick questions. Frick. All right. A Newton is equal to which of the following? A kilogram times meter per second squared, kilogram times meter per second squared, or kilogram per meter per second.
Jesus Christ. So a Newton is like one, I'm pretty sure, gravitational. It's relative to like Earth's gravity, I'm pretty sure. Mm-hmm. But as to the actual calculation of a Newton, dude. So it was, read them again.
Okay, a Newton is equal to which of the following? kilogram times meter per second squared, kilogram times meter per second squared, kilogram per meter per second.
I think it's A. Final answer.
That would be incorrect.
Son of a bitch.
So you guessed kilogram times meter per second. It is kilogram times meter per second squared.
Oh, okay. It was the square.
All
Son
right.
of a gun.
All right, here's your senior year, right? You're about to yeah. If you were to increase the mass of an object in motion, the net force required to keep it moving at the same rate of acceleration would A, increase, B, decrease, C, stay the same because the object is already in motion, or D, be zero because the object is already in motion.
What? Read the question again. Dude, I would flunk a high school because I'm asking the teacher to say it again over time.
If you were to increase the mass of an object in motion,
Increase the mass.
yeah, of an object in motion, the net force required to keep it moving at the same rate of acceleration would increase, decrease, stay the same because the object is already in motion, or be zero because the object is already in motion.
Okay, so for an object moving in motion, if you were to increase the mass of it to keep the velocity the same, you would have to do A, B, C, or D, right?
Say that again.
For an object in motion, if you were to increase the mass of it
Yep.
to keep a constant velocity with the mass increase, you'd have to
do one of these things.
Okay.
You'd have to, in relation to force.
Oh, to increase the force?
The net force would do what?
Oh, the force required to keep it
At the same
at
rate
the
of
same
acceleration.
velocity with its mass increased. The force required. Well, and what was C? Sorry, do nothing.
Stay the same because the object was already in motion, and then D was be zero because the object is already in motion. So would the force be zero, or would it stay the same as it was, or did it increase or decrease?
What increase?
That's right.
Yeah. That's obvious once I ask 18 questions. Yeah.
All right. This one, I don't think this one's that bad either. So this is the last question of 12th
This
grade.
is literally Newton's equation. F equals ma. Force is equal to mass times acceleration.
Exactly.
Yeah.
Dummy.
Yeah. Idiot.
The velocity of an electron in the innermost orbit of an atom is zero, mean, lowest, highest.
The velocity of an electron in an atom's innermost orbit?
Yeah.
Well, God, this is why are they teaching this? This is pre-quantum mechanics. The velocity is, well, I guess it would still apply. So read them again.
Relative to the other electrons. Anyway,
yeah.
The velocity of an electron in the innermost orbit of an atom is zero, mean, lowest, highest.
So the closest to the nucleus would be the lowest energy state orbital. And energy and velocity would be the same, or a higher velocity would equal energy, higher energy. So it would be lowest. That's the lowest energy state, ain't it?
It is highest.
Oh, did I have it fucking backwards?
I think you got it backwards.
Is the highest energy state the valence electrons?
No, the highest would be the innermost.
The lowest energy, lowest energy
Well,
state.
I mean,
is
it
the valence
kind of
electrons.
makes sense if you think about the pull of the nucleus, don't you think?
Oh, okay, yeah. Thinking about it like it's a planet,
Like an orbital type situation, even though it's
okay.
superpositions and all of
Yeah,
that.
even though it's all of them all at once. Yeah.
All right, one last
Okay.
question. So this is the college question. You're not as smarter than
I've already
you
failed
lost
it.
twice now, but
Yeah.
I will say this question, this might be super intuitive for you and you answer right off the bat. This one kind of got me a little bit. I had to like do a little Googling to understand this, and maybe it's just I'm an idiot, but okay, here we go.
Okay.
When a 100 Newton force acts horizontally on an 8 kilogram chair, the chair moves at a constant speed across the level floor. Which statement has to be true? A, the chair accelerates at 12.5 meters per second squared. B, the applied force is greater than the frictional force. C, the friction force is 100 newtons. D, there is no friction between the floor and the chair.
It's obviously not D. What was C again?
The friction force is 100 newtons.
And then B was...
The applied force is greater than the frictional force.
B.
Do you need me to read the question again?
Sure. Well, the question was if there's a 100 kilogram or a 100 Newton, what was it? 100
Newton
100 Newton force pushing a chair
of 8 kilograms, which that doesn't matter too much, but yeah.
Yeah, 100 Newton force pushing an 8 kilo chair horizontally across the floor.
Yeah.
What statement has to be true of it?
When a 100 Newton force acts horizontally on an 8 kilogram chair, the chair moves at a constant speed across the level floor.
Yeah.
And your answer is B.
Well, the B was the...
The applied force is greater than the frictional force.
Because if that were ever false, then the chair wouldn't be constantly moving across the floor.
That's what I said, and that's wrong. Let me tell you.
Really?
Yeah.
What?
So this confused the frick out of me until it didn't. Okay. So I was like, what the frick do you mean it's not right? So here's the correct answer. The frictional force is 100 newtons. Here's the thing. Here's the trick of this. It's traveling at a constant speed. So the force is 100 newtons and the frictional force is 100 newtons. My thought was, they'll just cancel each other out and it won't move. But that's not the case. Because it's still moving, it's just not speeding up or slowing down. It's constant. Because the frictional force is taking out any counteraction.
Oh, if there was a heavier frictional force, it would slow down.
Yep.
If there were less frictional force, it would speed up. Because it's a constant.
If the applied force was greater than the frictional force, it would speed up.
Yeah. That's what acceleration is.
Yep.
Yeah, that makes perfect sense.
That one got me.
Yeah, that got me good. Well, now that you explain it, that makes absolute sense. Yeah.
Yep.
Dang! I'm so stupid. Okay. Well,
that's it.
I need to skedaddle here because I got places to be and things to do. So we don't know what we're going to do next episode, but be excited for it. So we'll talk to you then.
See ya.